Okay, well, thank you for having me then. I'll start. Um, and the topic of my talk today is mobile autonomous pods for electric vehicle charging operations. My name is Wilco Burghout. I'm an associate professor at KTH in the same department as Eric Cornelius, that you have met. And the work that I will be presenting today has been largely done by a PhD student that I am the main supervisor of, Mot Ayman Khan, Ayman. And I got him to give us a quote. So, how will electric vehicles charge when vehicles go fully electric without filling the streets with chargers? And he's halfway his PhD project. So he did his licentiate, which is a Swedish title, um, encompassing three papers. And I will go through those, the main subjects in there. So I will give you an introduction. The first paper was a review paper, leading into different kinds of categories of EV charging and how they compare against each other. Then he built a simulation framework on top of maybe you might know Sumo, simulation of urban mobility, which is widely used in the academic and even outside academic projects. An application to city buses in Stockholm, electric city buses. How can you electrify them, keep them running with smaller batteries? And then some future research directions. I know that there is a time for questions, and I think a number of students have already uploaded some questions as well, which is very nice. So we can take them afterwards, like after my planned 40 minutes. But if you have a burning question, just interrupt. I have no problem with that. Yes. So let's start with the rise of electric vehicles. We all see this. There has been an increase and an increasing uh, level of electrification in specifically in passengers and public transportation, both in China, in Europe. We see that in elsewhere as well, which at least in a direct sense reduces the emissions from such vehicles considerably. And there are several European countries that have different plans of come to full electrification of either the bus fleets or the total vehicle fleets. And this 2030 is a moving target, and we expect it to be moved. But this is a clear target and a clear motivation to look, okay, if we're going to go for full electrification, how should this be? Now, before we go further into this, automation, which was an incredible hype until a couple of years ago, and now we don't hear so much about it, but it keeps on going, and it is basically slowly creeping up on us as more and more vehicles, even consumer level vehicles, without so much as advertising it, have actually some level of autonomous driving. Any new vehicle that has autonomous braking has 90% of what it takes to do autonomous driving, especially if they also have like lane keeping and auto steering. Um, so Mercedes is bringing this out explicitly now. Waymo has introduced robo-taxis for public use in multiple cities, many in the US, but they're coming to Europe as well. In China as well, there are a number of companies that are offering autonomous robo-taxis, and the same for Tesla. Now, this automation, electric automation, gives gives us opportunities. It also gives us restrictions, and it also allows us to start thinking out of the box. And what I mean with that, you will see a little bit later. Um, Apart from that, it allows us to start dreaming up new kinds of transportation, modular transportation or pod-based, and maybe transportation that goes over both road and rail, or maybe even using waterways, maybe using um, airways, or a combination of that. And it allows us maybe to a larger degree to go towards shared mobility. So mobility where you don't need to own your car as much, but still have 90% of the freedom that you get by owning a car. And as I said, these modular vehicles allow new ways of thinking, maybe platoons that move, that merge together and disperse when they need to get you to your final destination. Since they're modular, they could also be used for other things in different, maybe for goods, for instance, last mile, first mile goods delivery. There's more and more e-commerce coming and more need for delivery. And especially if this delivery is off peak, meaning say during the evenings or nights when you don't have so much passenger traffic, this allows for new ways of thinking of transportation. But all of this transportation, what we are currently thinking about, is all electric. All of our new ideas are electric. So how do we go through electric? The electrification paradigm shift in an optimal way, and how can we realize these expected or hoped for benefits? So electric buses, this is a reference. So electric buses are reduce not only emissions, but are supposed to reduce the costs of running buses by up to 70%, according to some optimistic research. Mostly based on the fact that electric buses have way fewer moving parts, are much easier to run for extended periods of times between maintenance, needs for maintenance. The same thing for freight transport. This reference was quoting up to $500 billion in the coming 10 years for freight transport in savings. I'm not sure how they came to that number. Critical services, normally we don't think about that, but if critical services can go automatically and have continuous operations, they can also be pre-positioned. There is some research going on about pre-positioning these kind of autonomous ambulances so that they can much quicker get to where typically at that time of day accidents happen. And like I already mentioned, urban logistics is hoped that we will have a huge benefit from this autonomous and electric paradigm shift. Now we can have lower operations costs due to lack of human drivers needed. We can have a higher utilization rate, and very many of this research that we see is like, yeah, they could actually drive forever. However, they still need to be recharged. So this seems to be a large constraint, the requirement of recharging these units. And already in many countries, I'm not sure if this is relevant in Germany, I know it's starting to become a political problem in the Netherlands, is the fact that already now adding more chargers to there in the network where you want them is becoming a problem. The grids were not designed for this kind of loads at these kind of places. So Ayman's idea was how could we think out of the box and think of a new solution? And sorry, I was forgetting that the routing, queuing, and charging times can increase travel times by up to 30%. There was some kind of news in Sweden. We always get snow, but we had like big snowstorms when you had them as well. And all of the electric vehicles, around 12% in Stockholm's region of the vehicles driving currently on the roads are electric. Many more of the new vehicles are electric. There were huge queues because the chargers, which normally are fine for everybody, now cost huge queues because of the low temperatures, and every charging session took 3 or 4 times as long as it would normally take. Now, on top of that, if you do DC fast charging, and this is a point of view also if you look at the life cycle assessment of these batteries, really increases the wear and tear on batteries. This is like a graph of the state of health as a function of how you charge. So the blue line is never fast charging, and like the red and orange bands are increasing levels of fast charging. You can see how the state of health degrades very quickly with high amounts of fast charging. So the research question that he put himself first is, okay, what are optimal charging methods? What is currently being developed? How do they stack up? How do they differ? Let's make an overview. So he read about 100 papers, and I will not talk you through those, but I will give you some of his conclusions and categories. Then he's saying, okay, but which charging method can improve travel times and allow battery reduction of these EAVs? And as you can see from the third question, it's like, how can these mobile autonomous charging pods be leveraged then to electrify urban bus networks, such as that in Stockholm, and then looking at the high frequency buses that have large capacity, and where adding extra chargers, say at the terminals, would come at a huge cost to the operator. Now this is, I'm going to move, I'm not sure if you see my Zoom window, it interferes a bit. This is the classification scheme that IMA made, so different charging technology divided up into static and dynamic charging, and then the static charging you can look at fixed charging, mobile charging stations. So the stations, say, think of a truck that you can place anywhere in the network to provide emergency charging, but it's still static charging. The truck will not move with you. Or battery swapping, which is becoming relatively popular now in China. There were earlier experiments that were so early in the life cycle of electric vehicles that they failed commercially. Yeah, but so those are the ones that he read up about. Charging lanes, there's been a lot of, especially in Sweden and the Nordics, has been a lot of research into electrified roads with either conductive or wireless transfer. A conductive transfer obviously is more efficient when it works. Wireless transfer less efficient, but maybe more flexible, especially if you have to deal with, you know, bad contact surfaces, snow, ice, etc. Dynamic battery swapping, so battery swapping on the move. And the last one is vehicle-to-vehicle transfer, which is what he concentrated on. First, so the static charging, you all know that, like the home charging or the charging on public chargers or work chargers. And they are widely deployed, and they will be part of any future electric solution, of course. What we are starting to see is that how many chargers can you really install? I mean, currently we are at a relatively low percentage of electrification, and already it seems like, especially in the bigger cities, that there are chargers everywhere. These are examples of the mobile charging stations, say trucks that will go and provide charge when they are needed, and different ways of doing this. For instance, battery swapping, which is a fast way. So the charging lanes, so either inductive or through conductive charging. This was a very hot area in Swedish research, but the Swedish Road Administration has looked at all of these results and frozen this development because it will be, one, extremely expensive to install, and two, which is the bigger problem, prohibitively expensive, they think, to maintain, you know, thousands of kilometers of electrified roads. So it doesn't look like we're going in this direction. Then we get to the vehicle-to-vehicle charging. Now, there are different ways you could do that. You could do it using a charging arm, like a robotic arm. So you follow the other vehicle. One provides charge, the other receives charge through a robotic arm that connects. Or you could do it wirelessly. Wireless is maybe more, requires less technology, less fragile maybe. On the other hand, it requires very close control it is typically more has more loss. And there are different ways in which you could do that, including drones. So you could have a truck with drones where the drones will land and provide charge to the different vehicles. There have been not only theoretical studies, there have been actually field trials with these as well. All of these technology obviously will need standardization, require additional investment in specific infrastructure, plus all of the control mechanisms needed to do this, efficiently, safely, and make it cost effective. So when he did the state of the art of this, he decided to focus on vehicle-to-vehicle charging, either wireless or conductive, which seems to be moderate in cost, moderately difficult to deploy, provide a lot of flexibilities, and some of it is already in development, either as a concept or actually as a preliminary product. So just to summarize very quickly, these are the main ideas. So the first is, why can't we, if you see the vehicle that the airplane is being charged while flying, you can see this idea is as old as we have fighter jets, really, really old. And we can do it in many different ways. If you see, this is actually a product that is being developed, the DiMag. It's a Chinese product as a battery on wheels, specifically for use in rough terrain, so think military operations. This is an AI generated image of basically a trailer that automatically attaches and detaches to buses and provides charges and then relocates itself. And the last one is a DHL concept vehicle being tried. If you imagine instead of having the DHL cabin just being a battery, this is the main idea for Ayman's research. So how should we study such a system that doesn't exist, with methods that don't exist yet? So we go to simulation. And Ayman did it in the simplest possible way he could think of. He said, okay, let's take Sumo, which is an open source microscopic simulation model, and let's see, what do I need to add? What do I need to program in order for this to study? And what would be the simplest way I could study this? And the simplest way would be a circular, or in this case, a big square network, where the client vehicles, they come in and they keep on driving in this circle until they run out of charge. Of course, we manipulate them so they run out of charge very often. So we need to charge them very often. We can study how that works and what kind of control algorithms would be needed for that. So these are parked maps. I will call them maps from now on, mobile autonomous charging points. And they're waiting for clients to pass, basically. And we put them at 4 locations around the network, and then we let the vehicles drive. Now, Shlomo by itself is not, it is flexible, but it cannot model this. So he needed to add a fair amount of code. I will not go into that code, but I will go into how it works. So you need some kind of algorithm that checks all the vehicles, say, okay, which vehicle needs charging? And then if you have a vehicle that needs charging, you say, okay, well, what is the nearest charging pod that has sufficient battery capacity? Then he reduces the speed of the client vehicle. This is just to allow for the charging pod to catch up efficiently and not waste half of its energy chasing a vehicle to charge. And then it starts charging and decides at some point to stop charging when the client vehicle has enough charge, or when the pod says, well, I need the remainder of my charge to make it back to my charging/parking spot. This is what it looks like. The red vehicle needs a charge. A pod detaches and now follows this vehicle and provides charge. It's as simple as that. And then at some point, it will detach and park itself at the next parking lot. Now, for the map operations themselves, from time to time. So in the beginning, it will go to the nearest parking spot, charge itself fully, and wait to be assigned. Now, if an EV comes close enough, it will then assign itself to charge a pod, and then it will share its energy and skip the next stops. There are a couple more algorithms that you need to put in, for instance, how to deal with the fact that it may get stuck in traffic. It may need to relocate to another position where pods are needed, etc., etc. And there are different ways of doing that. I will also not go into too much detail there. This is the baseline algorithm, really simple, where you see the pod chasing the client vehicle and wasting a fair amount of energy. And this is a smarter algorithm where the MAP will actually wait and deploy it at the optimal moment to get connected. This is basically what we implemented for the buses, and which is way more efficient. He developed a paper that I will not discuss, which uses different optimization methods, including reinforcement learning and MILP, that he will be presenting next week in Egypt at the IEEE FISTS conference. Again, that would take another 40 minutes to explain, but there are different ways basically you can optimize this control algorithm. Let me move to the next. Yes. So these are the experiment specifications. So we assume a modest capacity, battery capacity for the EVs, for the client EVs. The state of charge level when the EVs come into the simulation is Gaussian distributed, normally distributed, truncated, of course. Otherwise, all the vehicles would come in and would run out of charge at exactly the same moment, and chaos will ensue. So we spread it out nicely. And we start with 5 MAPs on each side, and we look at the efficiency. So how much of their energy do the mobile autonomous pods use by themselves, and how much can they actually supply? And if we then compare these two algorithms, clearly, this is mostly to show that the way, not only doing it, but the way you actually deploy these MAPs make a huge difference in the efficiency. And here we looked at how many vehicles can we safely support. So what you can see here is that if you go past 60 vehicles, from time to time there may be a vehicle in danger of running out of charge with the baseline algorithm. With the modified algorithm, you will start to have that much later. So this is a different figure. This is the amount of discharge you can allow per vehicle. So we studied this efficiency and the amount of vehicles that run that can be supported, and we find that this is the impact of these pods on the traffic. We studied that as well. I'm trying to go a little bit faster, otherwise I'll go over time. And he finds in that paper that the maps can provide V2V charging with around 70 to 80% efficiency. So they, depending on the algorithm, they auto consume about 20 to 30%, which is not great, but it means that it may be feasible. And even with this kind of setting and a rather simple, these were with the simple algorithms, the battery capacity of these electric vehicles could already be reduced by 14% with the use of maps. Average speed increased by 6% compared to static charging. And obviously a lot more compared to battery swapping. So rather, the results were a bit disappointing. We thought that we thought it would give a lot more benefit to the continuous operations. So, okay, well, let's now look at a more realistic case. A realistic case in the way that these are the bus lines, the electric. Some of them are electric now. Some of them, I think, around 55% of these buses are already run electrically. in Sweden. These are the high frequency bus lines that they transport a lot of people. And the biggest problem is that the electric buses that they currently have cost like 3 times as much as a hybrid, which they would otherwise use. Not only that, they are so heavy that they need to reinforce all of the bus stops and other places, like in front of traffic lights where the buses are stationary, because the buses are suddenly twice as heavy because of these huge batteries. So this was a problem brought up to us by the Swedish, the Stockholm region public transport authorities. Said, like, actually, this is a problem for us. We want to electrify, but it's hugely expensive in terms of buses, in terms of investment. It's also already creating problems to charge all of them at the same time at the depots. So say, okay, this idea of having mobile charging ports, maybe you could do that with the buses. Now, what we did is we used Sumo again. We put in, we took, maybe you know this, GTFS data. Almost all public transport authorities publish their schedules and sometimes also their real-time data in this format. So AVL is automated vehicle location. And we use those data sets to provide realistic schedules, the real schedules actually. And I say, okay, assuming that we have a 5-minute turnaround time, which seems to be the average, mostly because the drivers still need a break. We then calculated what would be the total distance traveled in a day for all of these lines in kilometers. What is the total energy consumed? And what is the energy per trip? How many trips will be done per bus? So how many buses do you need in order to run this whole services? And then we calculate, okay, currently we take the buses that they have currently, which have a 470 kilowatt hour battery. Typically they're Volvos, I think, mostly. The weight of the buses, the average running speed of the buses. So this is without, this is with stops at traffic lights, but without the stops due to taking on and offloading passengers. Typical energy consumption for this type of speeds, and we enforce a minimum turnaround time of 5 minutes. Now, if you then look at, if you only do depot charging, if you only charge at the depot, we see that most of the buses need a larger battery capacity to be able to run all day, which is typically what SL, the authority, tells us as well. So they can run the buses typically until 4 or 5 p.m. Electrically if they're fully charged overnight. And this is the total battery capacity then per line. So in order to safely run these operations and to be able to run until 8 o'clock, we said, okay, until 8 o'clock we want to run. So we didn't, the last runs we didn't include. We would need to increase the battery capacity by another 30%, creating even larger structural problems for them. Now, if besides the depot charging, we put a fast charger at each end, each turnaround, each end station. Let's assume it is possible, which is, if we start to look at the network, not very easy to do. Then already we could reduce the battery capacities for it, specifically lines 2 and line 6, which are the shorter lines, by a significant amount, by 50% already. And now we say, okay, what if we, instead of doing this depot charging, what if we do these maps? And these maps will be deployed in a specific way. I will first explain how the algorithm was changed, the map charging algorithm. So the maps will park at a specific spot that we design, and make sure that it has, before it gets deployed, that it has enough charge. When it has enough charge and there's a bus that passes by, it will be assigned and travels with the bus, basically. And, does the turnaround and make sure that it doesn't run out of energy itself. It also makes sure that it shares enough energy to the bus, and then stops charging if some condition is met. So either if it is at the station, at its end station of its charging route, or if there's another bus that needs energy more desperately than the current bus. So it's a slightly modified area. And these were we defined. This was calculated basically from the numbers I gave you. Say, okay, well, given the amount of energy, given this transfer speed, which is realistic, these were the operation ranges for these MAPs, and typically they're at the end of the line. Why at the end of the line? Well, at the end of the line, if you have a 5-minute turnaround here, you have a 5-minute where you can transfer energy without having to drive yourself. So typically, any solution that has mobile charging will probably make optimal use of the times when you're actually not moving, because it's the most efficient phase. When running this through the simulator, we were looking at what are now the required battery capacity. First of all, is it possible, and how many MAPs do we need? And we found that with 2 MAPs per line, one at each side, this would be largely enough. And we could further reduce the battery, specifically for the shorter lines, with quite a lot. So 67% compared to the baseline, with the depot-only charging, or 32% decrease in battery capacity compared to the depot and end station charging I talked about earlier. But if you look at the life of these maps and what they do when they charge, you could see actually most of the charge was delivered at either bus stops where they needed to stop anyway, or at the turnaround point, right, where they were standing for 5 minutes. So the driver could go to the toilet and take a cup of coffee. And this is all very nice, but now at the end of that third paper, he said, okay, but let's calculate, would this make any economic sense? Like, giving reasonable costs of installation. So everything was in there. The total cost of ownership is typically, you look at the cost to install the chargers, the grid connections, which are, as you see, considerable cost. The cost of battery replacement, because we are assuming an 11-year of operational life. This typical replacement rate for buses. We explicitly put in the maintenance cost specifically for the maps. It's this purple thing, and we put in the maintenance cost for the chargers as well. And looking at this and adding it all up, so in this case, it would be a lot cheaper to run this depot and maps compared to running depot only charging or the depot plus end station. And this is mostly because of, as you see, the charger installation, this really high capacity charger installation is hugely expensive. And these are one of the costs that we have not seen going down. The cost of batteries we have seen going down. The cost of many of the components we have seen going down, but not the cost of actually installing and providing grid capacity, because it is that is old technology that doesn't actually evolve very much. I mean, it still requires just basically digging up big parts of the road and installing huge capacity cables there. And typically where you want them most, meaning no deviation from the bus route, is where you are least capable of installing them. So yeah, this is a considerable reduction in cost if you would deploy this. So one of his conclusions is that this may actually be a viable solution, probably not just by itself, but it might be a complementary solution. And one of the things that we haven't looked at is the flexibility and reliability of these bus networks. So if you start reducing the batteries, but stuff happens, like I said, You have a big winter storm and suddenly your battery quickly runs out of charge uh, halfway through your route. Then you can send one of these maps to provide energy quickly. Same thing for other vehicles, client vehicles or normal vehicles running out of battery somewhere in the network. You could quickly send one of these maps to charge it. What we didn't do, so what we did do is we did back of the envelope calculation to say, okay, what would be a reasonable way to implement this? We didn't optimize many things. There are many things that can be optimized. Like I said, Ayman is presenting a paper about using this operational optimization. So the on-the-fly decision making. So, okay, which bus should I charge when, for how long, and which MAP should I send there? But there are many more things that can be optimized. And this is, for instance, one of the things, the optimization of the location of the MAPs. For instance, why not placing them at crossroads between different bus lines? Since if you have many clients here, this is how you would define any kind of market. Maybe this would be a more beneficial allocation of this map operation area. You could also look for long bus lines or for other types, such as city logistics or maybe long distance trucking. In Sweden, long distance trucking is really long distance. And this is one of the areas where electrification is still lagging because, you know, in order for a huge truck to be able to drive 1,000 or 1,500 kilometers without stopping, it needs to use maybe half of its available loading capacity as a battery, which is unacceptable. So this is these are areas that we will go into soon. Sorry. And I managed to stay within my allotted 40 minutes. This is my email address. This is Ayman's email address, and you're welcome to provide any further questions, or if you want to continue this discussion after today.